This is Chapter 3, Example 6 problem. Here we have a piston cylinder assembly contains 2 kilograms of water at 100 degrees Celsius and 1 bar. The water is compressed to a saturated vapor state where the pressure is 2.5 bar. During this compression, heat is released to the surroundings. And we're going to neglect some kinetic and potential energy. So for this problem, we start out with our engineering model. So we have our known. Okay, and there we have a, we're looking at this and we're like, okay, we have a piston cylinder assembly filled with water, undergoes compression, and releases heat. All right, so here we're looking to find a few pieces of information, basically just one, work. We'll have to find other information in between. But we're going to be looking for work in kilojoules. Okay. So we have a piston cylinder, and we're going to neglect kinetic and potential energy. So I'm going to draw it this way. And we know we have some water in it. There's 2 states. State 1, we know there's 2. The mass is 2 kilograms, and that's at state 1. Temperature is 100 degrees Celsius, and the pressure is 1 bar. Okay, the water is compressed to a saturated vapor state, and the pressure at state 2, if we're looking at state 2, is 2.5 bar. During compression, heat is released, and the heat released, I'm going to draw it down here, is 250 kilojoules. Okay, so those are our 2 states and some information. We have to make some assumptions. 1, it's a closed system. We said that kinetic and potential energy are negligible. All right. So if we look at our energy balance, and with our assumptions, we know that kinetic energy and potential energy are 0. So this term here, heat is given. We're asked to find the work, so that's what we're looking for. So how, right, that's what we're looking for. So how do we find Q? Okay, and we're given some pieces of information. One thing we do want to look at is a temperature. They gave us the temperature, our specific volume, and to see where we are. Okay, so one thing to look at is we can look at our tables, and for one, right, if we're at 1 bar, so our lines here, if this pressure right here is equal to 1 bar, what is the temperature at 1 bar? Okay, so let's look at our tables. And here's our pressure table. And our pressure table, this is 1 bar. And our temperature, so the temperature right here is 99.63 degrees Celsius, right? But we want 100. And 100, if we look at 100 going across our graph here, 100 is out here. And that is state 1. And since we're out there, we're in the superheated region. So we need information off the superheated table for that one. So let's look at a superheated table. And here we're at 1 bar over on the second half of the table, but the temperature is way over on the left. And at 100 degrees, we can see we have some information here that we could use. Okay, so 1 bar and 100 degrees, we can use our specific volume or the specific internal energy. And since we're trying to find U, we definitely need our specific internal energy. So I'm going to write that down at state 1 off this table. This is 2,000.67 kilojoules per kilogram. And just so I don't have to come up with that table again, in case we need the specific. So we have the information for state 1, okay? So then let's see what happens. So we're going to compress to a saturated vapor state at 2.5 bar. Say 2.5 bar is up here, right? So that's 2.5 bar, and notice we are at a saturated vapor right here. So that is state 2. So we're going from state 1 to state 2 in the compression direction, right? We're decreasing the volume. And so for that information, we need the saturated, and I'm going to get it for both of these, the saturated vapor internal energy and specific volume. So let's look at our table that we had before. And so for 2.5 bar, which is right here, we have our saturated vapor for our internal energy and for our volume. So we're done with the table, and we can solve our problem, right? We want work, and so I'm going to rewrite this here without the potential and kinetic energy. We want work, so I need to add this work to both sides. And I need to subtract our internal energy from both sides. Now we don't have, and this is going from state 1 to state 2 in each of these cases, right? We're going from state 1 to state 2. And so let's think about our internal energy. We have specific, so we have to divide that by mass or multiply the specific internal energy. And this is from state 1 to state 2, so it's our final minus initial. So we're going to go ahead and substitute that into our equation here. Q12 minus the mass of our final minus our initial state. Okay. Let's go ahead and put all our numbers in. So we have our heat, right? And we have our heat, which is 250 kilojoules. We are given the mass that we have 2 kilograms and the 2 internal energies. The saturated or state 2 minus state 1. Now we can calculate our work. And when we calculate our work, things to think about before we go any further is look at our Q. Our Q is going out. So we always have to make sure we have the correct sign on our Q. And because it is giving off heat, that is negative. So we got to make sure we have our negative sign there. Now we can go ahead and do our calculation. And we find that when we multiply this out, this is 311 kilojoules. So work, which makes sense, right? Negative, work done on the system, because we have a negative value, right? We're pushing the piston in on our gas, which was a gas, and now is going to be a saturated vapor, and our water is our system.